In this chapter, we are going to study magnetic field produced by electric current. Ørsted first discovered that magnetic field is produced by an electric current passing through the wire. Later, Gauss, Henry, Faraday and others showed that magnetic field is important partner of electric field. Maxwell's theoretical work highlighted the close relationship between electric and magnetic field. This resulted into several practical applications in day-to-day life like electrical motors, generators, communication systems, computers. In electrostatic, we have considered static charge and the force exerted by them on other charges. Now we will consider force between charges in motion. In 10th standard, we have studied when magnetic needle is held close to the current carrying wire, it shows direction of magnetic field around the wire. And to know the direction of magnetic field, we have studied right hand thumb rule. How right hand thumb rule help us to understand the direction of electric field and magnetic field. Imagine this is current carrying wire. Okay, the direction of current is in this direction. So suppose this is the wire. What do we have to imagine? The current carrying wire is grabbed with your right hand. So this is right hand and the thumb is pointing in the direction of current and your fingers curl around in the direction of magnetic field. So thumb will give you the direction of current and this curled finger will tell you the magnetic field around that wire. So here we have diagrammatic presentation. So here you will find this is the wire, current carrying wire. So the direction of current is upward. And as we have studied, the thumb will give you direction of current and the curled finger will give you direction of magnetic field. So here this is the showing the direction of magnetic field. So what is the effect of current carrying wire on other current carrying wire? If we have two wire like this, suppose this is first wire in the current in this direction and another wire, suppose the current in this direction, will be there any effect? So here I have, suppose this is your first wire and this is your second wire. So they are separated by some distance and the current is moving in this direction. So what we will do, first of all we will find the magnetic field around this. So if you could see this, what rule we use? Right hand thumb rule. So this thumb is in this direction and this magnetic field is going into the paper. By using vector notation, we can use this cross when they are going into the paper. So suppose the magnetic field which is around this will be in circular shape, will be like this. So this cross will tell you they are going into the paper. And my fingers are going into this paper and coming out of this paper from this side. So coming out of this paper from this side. So we use this kind of notation when the field is coming that vector. So we know that magnetic field is also a vector quantity. So I can say these are coming out of the paper. So this is the current carrying coil, current carrying wire. So through this current is flowing through this wire and around it. So like this the current is coming out and in this current is going and like this. So this is direction of magnetic field and it will go on like this, like this. So from here this is the field of that magnetic field. Now what we have to check, if I am going to place another current carrying wire like this, so this is our previous one, will be there any force or any other thing that experienced by this another wire. Okay, so let me draw that another wire. So suppose this is another wire, current carrying conductor, suppose same current or different color current. Again, by using right hand thumb rule, what we can find, they are moving into the paper. So for this, suppose I am going to use this pencil. So this is magnetic field which is going into the paper for this wire, and it is coming out for this. From this side it is coming out. Means from here this A is going like this and it is coming like this. So both this A is up by using right hand thumb rule. I can say this is the direction of magnetic field. So what we can do, we will consider our right hand. So this index finger will tells you the direction of magnetic field. So it is going into this paper. So as we know that the current is flowing in this direction, so the direction of electron will be in this direction. Electron is a charge when they flow, so opposite of that is nothing but our current, direction of current. So suppose this middle finger will tells you direction of electron like this, which is downward, and this forefinger will tells you the direction of magnetic field. The third means the thumb will tells you the force experienced by second wire toward first wire. So the direction is in this direction. Okay, so what I can say, the force is in this direction. So this is direction of force. So if I consider in this way, this is middle finger shows you direction of this charges, and this finger will tells you, forefinger will tells you the magnetic field. When I will use this will tells you. So here you can see like this. So this is the magnetic field, this is the charges, motion of charge, that is electron, and this will give you force. So from this description, what we understood, that velocity of electron, that is charge, and magnetic field and the force experienced by that wire are perpendicular to each other. Means they follow vector cross product. They follow vector cross product. So from this I can write, so here I am talking about electron. So charge on electron is minus E, moving with the velocity vector v. So from that I can say the magnetic field means force in magnetic field, suppose Fm, force in magnetic field is equal to charge and cross product of velocity of charge and magnetic field. In general, if we say the charge q in this field, means in magnetic field, I can write Fm, vector Fm is equal to q vector v cross vector b. So that charge could be any charge, positive charge or negative charge. What it tells you, that if both electric and magnetic field are present, the net force on charge, when both electric and magnetic field is present, the net force on charge will be given by, in electric field, q vector E, and in magnetic field, q vector B cross vector v cross vector B. Means this is the force on charge q in electric field. So I will write like this, Fe, plus this is force on a charge q in magnetic field. So for this we can understand by watching a small demonstration, but for that we have to understand which force is this. This force which we describe here is called as Lorentz force. What we will call it as? Lorentz force is the force exerted on a charged particle. The force exerted on a charged particle Q moving with velocity v through an electric field E and magnetic field B. So Lorentz force exerted on a charge moving with the velocity v in electric field and in a magnetic field B. If velocity v of a charged particle is parallel to magnetic field, v is parallel to magnetic field, then the magnetic force, that is magnetic force, will be equal to 0. The magnetic force will be equal to 0. And if charge is stationary, if charge will be stationary, so its velocity will be 0, and as its velocity is 0, so this 0 cross B will be also 0, even if magnetic field will be 0, means this F will be equal to 0. If your magnetic field will be 0, still its F will be equal to 0. So from this equation we can say the force on the charge due to the electric field, it depends on strength of the electric field and magnitude of charge, because this factors get 0. And magnetic force depends on velocity of charge. What we can say, this magnetic force depends upon velocity of charge. So from this we can say that vector v and vector f are always perpendicular to each other, and therefore their dot product will be equal to 0, because cos of 90 degree, because vector f dot vector v is nothing but fv cos theta when they are perpendicular. So cos 90 is nothing but 0, so you will get cos 90 is equal to 0, so you will get Fv 0, that is equal to 0. Magnetic force Fm is perpendicular to displacement, and that's why the magnetic force never does any work. Means magnetic field never does any work on charge. If magnetic forces changes the direction, but it changes the direction of motion, it does not do any work, it just changes the direction of motion of charged particle, but never affect the speed. So from that we can say magnetic field vector F Q vector V cross vector B, if I solve this, what you will get? Q, the cross product of this is nothing but magnitude of this vector V cross vector B and unit vector. So this is nothing but Q, this is nothing but VB sin theta n cap, where n cap is unit vector and theta is angle between vector V and vector B, and its propagation, that is vector V cross vector B, will be given by this third mutually perpendicular axis, which is in the direction of force. So if the force is 1 Newton, acting on a charged particle of 1 coulomb moving with the velocity of 1 meter per second, from that what we will get? B is equal to F by QV, and therefore unit of B is Newton second per coulomb meter, and dimension of B can be calculated by dimension of F divided by dimension of Q and dimension of V. So SI unit of this magnetic field is also equal to 1 Tesla, and the value of 1 Tesla is equal to 10 to the power 4 Gauss. Now we will see the small demonstration that when we connect two wire to power supply and flow the current in same direction, then you will find that the wire move closer to each other, means they attract to each other. They attract each other as soon as current start. The force in this experiment is certainly not of electrostatic origin, even though the current is due to electrons flowing in the wire. The overall charge neutrality is maintained throughout the wire, hence the electrostatic forces are ruled out. Now we have connected power supply in a such a way that the current in both the wire will be flow in opposite direction. So then you will find when the current passing through them is opposite, they repel each other.